So I'm Chris, the project manager, and I'd like to start by providing some context around the project. So by way of background, a 2024 industry survey found that around 95% of refrigeration systems continue to use high global warming potential synthetic refrigerants. So that represents a significant or substantial emissions liability. And so it was decided that we should address that challenge, and a project was initiated. So when we started the project, we first agreed on a long-term outcome, and I have put that here on the slide: a sustainable and resilient model for decarbonisation of the kiwifruit industry's refrigeration systems, with the benefit of enhanced global standing for New Zealand's largest horticultural industry. So we use this high-level outcome as the foundation for the project scope, and also for allocation of funding. And to decarbonise, we've been focusing on 3 specific actions, focusing on the refrigerant. So switching to natural refrigerants, substituting older refrigerants in existing systems, and securing leaks, or securing the system against leaks. Today, we're going to focus on the first 2 of those. That's the system substitution and the gas substitution. And it's important to note that the material for this webinar is based on 2 reports for the wider project. And rather than covering every detail in the reports, we're just going to be covering the headline findings and the most significant results. So please feel free to submit questions through the webinar Q&A at any stage, and we'll try and address as many as we can at the end. And with that, I'd like to hand over to Dave and Tony to take you through the findings.
Great, thanks, Chris. Hi everyone. So my name's Dave Taylor. I'm a consultant here at Deta. So I've had about 25 years in energy efficiency, system optimization, and decarbonisation. So today I'll be talking about the natural refrigerant side of things.
Yeah, I'm Tony Arnott. I'm one of Deta's other consultants. I've got around 24 years experience in a range of industries. And yeah, I'll be looking at the drop-in replacements for this particular webinar. So if you want to jump on to the next slide, Dave. So Chris alluded to the 2024 refrigeration survey. This was looking at the kiwifruit industry specifically, and we had fantastic participation from the industry with an estimated 97% by kiwifruit volume participating. So that was excellent, almost unprecedented to get that level of buy-in. So that was great. So that was looking at what the existing refrigeration fleet is that's out there and a few of the different factors around it. So one of the key findings was that there's an estimated 176,000 tonnes of carbon dioxide emissions equivalent worth of refrigerant on the different kiwifruit packhouse and cool store sites. That's, to put that in perspective, that's about the equivalent of burning 87,000 tonnes of coal. So pretty substantial. And it indicated, the survey, that there's a high reliance on hydrofluorocarbons, HFCs, particularly R404A, but also a surprising number of R22 systems still out there, which was quite interesting to see. And those 2 combined represent around 62% of the total emissions liability for the fleet. Another interesting finding was that of the reported leaks over the recent period before the survey was taking place, there was around 7,000 tonnes of carbon dioxide equivalent emissions per year. We think the actual number is likely to be quite a bit higher than that, because they're fairly incomplete record keeping at that time, quite variable from site to site. So we just jump on to the next slide. So when we're looking at these particular initiatives, there's kind of 2 main drivers for why we want to move away from high global warming potential refrigerants. So the first one is that there's actually an HFC phase down underway, and that's where there's like a gradually lowering cap on how much emissions can be imported into the country in the form of refrigerants. So that has the effect of increasing cost in general for the high GWP refrigerants such as R404A. And it also adds risk around availability, whether or not you actually be able to get replacement refrigerant if you need it. The second factor that's pushing change is desires for emission reductions. And that can come either from internal targets being set by the kiwifruit packhouse cool store industry business, or it can come from outside the business through the supply chain, demands from customers wanting to reduce their carbon footprint, and a need to continually improve our marketability, particularly to the European market. So that's setting the scene for why we want to move away from high GWP refrigerants. If you want to step on, Dave. So I'll pass back to Dave now to talk about natural refrigerants, the first kind of half of what we're talking about in this webinar.
Great. Thanks, Tony. So there's the three key things that I'll be talking about today. It's around the refrigerant options that we've got on those natural refrigerants, and the system architecture for those refrigerants as well, and how they differ between different options, and also the solution longevity. So if we're spending this money, what does it actually get us in terms of life for the system? So when we're looking at the natural refrigerants, the first one we're going to be looking at is ammonia. What I should actually say is that they are natural refrigerants because they're found naturally in nature, so they are around in the world. That is different to synthetics, such as HFCs and CFCs. So ammonia and these other ones are fit into that natural side of things. So in terms of ammonia specifically, it is widely used around the country, in particular in large installations, so such as meat plants and milk plants, and certain commercial side of things as well. It's got some good pros around it, so zero ozone depletion potential and global warming potential, which is great. And it's got quite a high efficiency as well. So given the thermodynamic properties of it, it does operate very well in compressors. And it is abundant and low cost as well, which is becoming more and more crucial as time and synthetics get more expensive. There are some significant cons as well. As we all probably know, it's a hazardous material. And this does mean that there's some quite stringent rules that need to be met in order to be able to use this. But I should say that they are quite doable. And as I said earlier, lots of sites do use ammonia. Compared to some other systems, it does have relatively high maintenance costs. So that is something to keep in mind, but that does is counteracted by some of the high efficiency as well. So overall, it does have a good operating cost. And given the toxicity of it and the hazardness of it, it really is down to have to be used as a primary refrigerant, with other secondary refrigerants actually moving the cool to and from the particular cool stores. The second one we'll look at is carbon dioxide. And there's been quite a lot of talk about this recently, but it's actually been in use around the world for a long time, since the 1860s. But it is getting more and more prevalent these days after, I guess, falling out of favour for a wee while. And one of the areas that it has been used a lot in the supermarkets, and there's a real push in supermarkets to take out their synthetics and put in the carbon dioxide. So some good pros again, so zero ODP and global warming potential of 1, which is effectively pretty much nothing anyway. Also high efficiency when it's operating in its general mode, which is subcritical. And it's abundant and low cost refrigerant. A couple of the cons, it does run at very high pressure. So where lots of refrigerants operate around that 10 bar or lower kind of mark. For CO2, we're looking at 60 to 70 to 80 bar part of the system. So that does need to definitely be designed for. And it can lose efficiency in hot weather as well. So it has a relatively low critical temperature of 31 degrees, which means that if the ambient temperature gets above 27 or 28, it moves into its transcritical mode, and that can cause the efficiency of the units to about half. So what we should say though is that studies have shown that, particularly for the kiwifruit industry in New Zealand, the actual hours where that does happen is relatively low, partly due to the timing of when the high loads are on the kiwifruit industry and just the ambient conditions in the country as well. So while it is a consideration, it's nowhere near a bigger one as it has been made out to be in the past. The third set we're actually grouping together are the hydrocarbons, the propane, isobutane, and polypropylene. And polypropylene is the most common of these that we've come across, in particular for the kiwifruit industry. So again, some good pros, 0 GWP and a global warming potential of 3. So again, very low compared to synthetics. And the relatively cheap packaged units, which is quite good. Some considerable cons as well, of course, though. So it's high flammability, and there have been issues in the past around fires and things from these, so it is something to bear in mind. And given the high flammability, the system capacities are limited. So generally these are smaller units, although operators and installers are trying to get larger sizes units to cater to a wider range of things. Also, given the high flammability and the limited system capacities, they are suited to a secondary refrigerant as well, really minimising the highly flammable side of things. And while the efficiency is not too bad, they are lower than ammonia and carbon dioxide too. So not as widespread as the first two. So if we're looking at system architecture and how these are actually installed, with the natural refrigerants, it will actually need a system replacement, and how far that goes depends on what's already into the cool store. So here, the first one we'll look at is direct expansion, and that effectively has the compressor plant outside the cool store, and the refrigerant is piped into the inside of the cool store, where it's put through an evaporator to cool the space down, and then the refrigerant is then returned to the compressor plant. On the other side, we've got a secondary refrigerant, and that is where we've got the compressor plant outside, and that feeds a secondary loop via a heat exchanger. So glycol is by far and away the most common secondary refrigerant in use. And so what happens here is the compressor plant cools the glycol down, and then the glycol does the cooling to the cool store. So in terms of direct expansion, some of the good things about it is a relatively simple system, so there's no secondary loop, which is good. So you have one set of controls and things, and that can make it easier. Generally, it will have a higher efficiency. Given there's no intermediate loop, it'll have a higher suction pressure, which improves the efficiency of the compressor, and also there's no glycol pumps and things like that. So in general, that is better. The evaporators in the spaces are normally smaller due to using the latent heat of the evaporation, and that can also be quite good in terms of structural considerations for the buildings. It's also very fast to respond to load changes, given the latent heat advantage that can really drive that. And as I said just earlier, the lighter piping and evaporators, which are good for these cool stores. Some of the cons, though, is that higher refrigerant charge, and that does mean that there is leaks, then you can lose a lot of refrigerant, and there is a greater refrigerant leak risk as well. So more piping under pressure, and more piping, more valves, they can all leak, and it does add to that. There can be a risk of accidental damage as well with those pipes in there. And I guess design of the cool stores is an important consideration to make sure that forklifts and things don't actually damage the pipework. And there is a worker exposure to refrigerant risks, refrigerant leaks as well. So that can be a problem. And I guess the risks with these, with I guess the root expansion really does limit it to CO2 rather than things like ammonia and the hydrocarbons. For the secondary refrigerant side of things, one of the really good pros around it is its stable temperature and improved humidity control. So given the relatively warmer temperature of the glycol within the pipe, the difference between the glycol and the room temperature is a lot closer, so that improves the humidity control. There is a reduced primary refrigerant charge as well, which is really one of the overarching goals for this, and given that it's just in the central plant outside. And it's very effective at long distance cooling distribution, so the glycol can be pumped around quite a wide range of cool stores over quite a high area, and you don't have any of those issues with the refrigerant quantities. And it really is a very flexible solution going forward. So once the internal systems have been converted to glycol or high glycol to begin with, then you can really do anything you want on the outside to the primary plant site. And it's nice and easy that way. Unfortunately, there are some cons as well, of course. There is a lower system efficiency generally, both down to that additional trim step of the heat exchanger and also the pumping energy consumption. So depending on the system, they can be substantial and they do need to be considered. There's often a higher capital cost down to the extra equipment as well. So that all adds up. And there is an increased system complexity. So that is something to bear in mind with the design. But it can be said all natural refrigerants and in general all refrigerants around can operate with that glycol system. So it is a good option to go for. If we have a side-by-side comparison of some of these options, both in terms of the secondary and primary refrigerants, and also the synthetics versus others. I've got those 5 options there. So I've got the synthetic glycol system in there as kind of a baseline. So that's assuming that a cool store is a glycol secondary system or has been converted. And then we're looking at the options 2 to 5 on those others. So as we can see, in terms of the operating cost, the CO2 direct expansion and the ammonia glycol are very low. So that's really down to the energy efficiency and how effective they are at that. CO2 for glycol is slightly higher, and that's really just round to the interim loop and the slightly lower efficiency of the CO2 versus the ammonia. Unfortunately, the hydrocarbons, the efficiency of that isn't quite as good, so it's more comparable to the synthetic options. In terms of the capital cost, it's kind of the opposite to what we saw in the OPEX. So both the CO2 and the ammonia are generally the more expensive options, and we'll talk about more later, but this really does help drive the decision making further down the track. And the hydrocarbons are kind of in the middle again. In terms of safety, hydrocarbon and the ammonia, they generally have the largest issues around the flammability and toxicity, and the others are not too bad. Emissions, and so these are purely the refrigerant emissions, no consideration for the energy emissions, more electricity, carbon emission side of things. As you can see, all the naturals are very, very good and by far better than the synthetic. And the solution longevity. So again, the synthetics, they do have a definite shelf life with the phase down that's coming through. So the natural side, they are good for the life of the cool store. So in terms of some key points from this, and in a retrofit scenario, the CapEx really is an important side of things. And one of the overarching ideas we found was the idea of extending the operational life of the cool store. And so if the cool store has a long life ahead, then it can justify the CapEx of the more expensive, the more efficient options. But if it's a shorter lifeline, then that's unlikely to be the case, and potentially some cheaper conversions can be done. And as I said earlier, the glycol cool store conversion, it is a great way to future-proof things. The efficiency of the CO2 and the ammonia are both very good. And in particular, there have been those concerns with the CO2 around the transcritical operation. it is well aligned to New Zealand for its operation, and really those concerns have been solved. Unfortunately, the real world data is not that around, not too much around, unfortunately. So it'd be great to see as these systems progress and more get in, some more monitoring done, so we can really see what's happening. And that final point is the hydrocarbons. We don't really see them playing a particularly large role in the future. The CapEx benefit compared to the others isn't really there to justify the risk, and in particular to the small operating size of the system, lots of different systems. So in terms of key questions around whether you go for a natural refrigerant or not, that first one really that we've talked about previously is the remaining serviceable life of the cool store. So if it's a long-term decision and solution you're after, going for those, the CO2 or ammonia are a very good option. But if it's more of an interim solution, probably something drop-in is more suitable. And what is the realistic utilisation of the cool store? So generally, the longer operating hours of the cool store, the higher the loads, and that can also justify the higher CapEx but lower operating cost options that we've seen. And does the site already use ammonia? So if there are already ammonia systems on a large site, then that can be a good way to actually to expand it out further. If not, there are some of those hazards and things that need to be covered off, which can be a bit challenging if you haven't dealt with it before. And a big consideration is the cool store structure. Can the cool store structure support the weight of the glycol piping? So there is some additional costs and requirements around that. And so if it can't, then that really does need to be considered around to what system you go for. And a big one we do come across a fair bit is around the plant efficiency and comparing apples for apples. So I've got the design conditions, but also the operating conditions that we're expecting to see. And it's important that they are compared similarly across different options. Otherwise, it can drive some behaviours which you wouldn't expect. And also very important to ensure that those ancillary loads are included. So if you are going for a glycol system, bearing in mind there are those pumping costs and energy use which can be substantial. And potentially the evaporators can also be repurposed as glycol unit coolers. So there's not a lot of data around this, but there is a push where it's possible to repurpose this as equipment. And where it can be done, it can reduce the cost, which is great. So really the three key points from today. The three main options for the natural refrigerants, the hydrocarbons, the ammonia, and the carbon dioxide. We don't realistically see the hydrocarbons as being widespread in the future, but it is still an option. But really the ammonia and carbon dioxide options will be good to go for. In terms of the system architecture, really direct expansion and secondary refrigerant are the two to go for. And they will be different around retrofit and new cool store applications as well. And unfortunately, there's no silver bullet. It really is horses for courses. So every site is different. Operating at different sites, the different sizes are different. All those things need to be considered and rolled into your objectives to know what you need to be doing. And that's me. Over to you, Tony.
Great, thanks, Dave. Just present on here. Okay, so drop-in replacements. The second of the topics we're looking at are drop-in replacements. So this is a work stream that I was involved in looking after. And this is where we're looking at what the real world costs, performance, and practicalities are around using drop-in replacements for high GWP refrigerants. This is the general idea here is that if you've got an existing system that's got a fair bit of life expectancy left, and you've got a high global warming potential refrigerant such as R404A, then you may want to look at replacing that refrigerant with a lower GWP refrigerant that can function in that equipment for the remainder of its life, to kind of continue the life of the equipment without having as much risk of emissions from leaks. So we actually did a series of pilot trials across 4 different KPHI industry participants. So there are 28 refrigeration systems altogether where the refrigerant was replaced. So we've got a pretty good sample size, and that actually represented 6,700 kilograms of R404A being recovered, which was about 35% of the total identified in the survey from 2024. So in all of those cases, the refrigerant was replaced with R449A, and that equates to a potential emissions liability reduction of around 17,500 tons of carbon dioxide equivalent. So that's pretty significant. Now, the key finding that we had, and this is kind of hot off the press, is that the energy performance, the efficiency of these units appeared to remain similar following refrigerant replacement. So we'll get into that, but that was quite a positive finding, as there's some consideration out there that it may sometimes worsen efficiency. So there's 3 key points we want to really get you to take away from the drop-in replacements aspect of today's webinar. And they are that, firstly, it's a simple option to reduce your global warming potential of an old system. Secondly, that there's a couple of key factors that really dictate a large part of how much your cost is to do these drop-in replacements. And thirdly, we want to emphasize that drop-in replacements are only a temporary solution, kind of for a transition period. They're a compromise, they're not perfect. So looking at the first part of that, drop-in replacements. So what exactly are they? So they are usually used to replace refrigerants that are being phased out, such as R22 or R404A. They are mostly blends of hydrofluoroolefins, or HFOs, and hydrofluorocarbons. So they're a mixture of the 2 types. So the HFOs are really the magic in that reduce the global warming potential of the overall mix, because the HFOs typically have almost no global warming potential. The benefit that this gives you is that you can keep using your existing assets while having a much reduced emissions risk. And the other benefit is that your refrigerants are generally significantly cheaper to replace if you do get a leak or you need to swap it out. Now, they are called drop-in replacements, but normally there are a few changes that you do have to make. So if you've got mechanical expansion valves, then you'll need to usually replace them with purpose-designed expansion valves to suit that refrigerant. And you're likely to also have to make some changes to refrigerant oil and filters and filter dryers. These are all possible things you may need to change. So just 3 examples of drop-in replacement substitutions that are relevant to the kiwifruit industry. We've got R404A and R22 can both be replaced with R449A. And we're just showing here the global warming potential of the refrigerants before and after. So effectively, that's cutting it by 67% for 404A to 449A. The drop's not very much for going from R22, but the key thing with R22 is that it's ozone depleting. So whereas R449A is not, so that deals with that issue as well. And then 134A can be replaced with 513A quite commonly, and that's just over halving the global warming potential. So just some examples. So the key decisions that you have to make when you're looking at drop-in replacements that dictate the cost, one of the 2 is whether or not you're going to upgrade from using mechanical valves to go to electronic valves. And this is something that sites will often consider. As you can see here, this is showing our comparison from the pilots as to how much the costs were for mechanical versus electronic. And it's a big difference. So if you're for the systems that were just going mechanical for mechanical, the costs were generally under 25K to do a whole cool store worth, a whole system worth. Whereas to go to electronic valves, they were above 75K. There were just 2 of them in our samples that really went this way for new electronic valves. That were in a straightforward kind of comparison before and after. So big difference in cost. But what are you getting? You are getting something different between the two. So mechanical expansion valves, or thermostatic expansion valves is their kind of proper name. They're kind of just a mechanical device based around a temperature sensing bulb that pushes on a spring to open or close a valve. So they're good in fairly constant duties, but if you've got quite a duty that varies quite a lot, that's where they're less efficient. And if you're doing a future refrigerant change to another refrigerant, then there's a good chance you'll have to replace the valve or at least the power head when that time comes. So that's kind of the general situation with them, but they are much cheaper. So then the electronic expansion valves, they consist more of a motorized valve with sensors and a real-time controller that lets the system actually control to a target set point. And that means that it's excellent at constant loads and also at varying loads, because it actually adjusts to get to the final target no matter what the kind of situation is, as long as it's within its kind of range of operation. And that means it's also conveniently very easy to change to a new refrigerant. You just adjust the settings. So the question isn't which is better. It's really a question, because electronic expansion valves are obviously better, but they are more expensive. So what you need to look at is, does the store justify the cost of going to electronic valves? And that's really around how varying your load is. The second big thing that influences the cost of doing these drop-in replacements is what you're doing around refrigerant disposal for your old refrigerant and supply of the new refrigerant. Because these refrigerants cost so much, and that's one of the drivers to move away from them, there's significant differences in how much your overall project cost is, depending on how you source and dispose of your refrigerants. Now, there are at least three refrigerant destruction service providers out there who can offer you different levels of support in different ways for projects that remove the high GWP refrigerants. The examples we've got here, they do vary over time, depending on the ETS price is a key factor that influences what they can offer. But the key takeaway here is to talk to the likes of these parties to find out what the latest is that they can offer you, and then make your decision based on your particular circumstances. So the examples here, CoolSafe, they'll pay you to take your refrigerant and destroy it, and they're able to offer better deals the more that you give them, just as general. So they're collecting a credit effectively that's tied in with the ETS system, the emissions trading scheme system, for disposing of those refrigerants. Ref Specs and Ref Destruct, they can at times, at least when we're talking to them, they can swap your old R404A or 507A for new 449A on kind of a like-for-like equivalent quantity basis, and then they'll destroy the old refrigerant. So that's one way you can go as well. A-Gas have a slightly different offering around being able to take your old refrigerant and reclaim it back to virgin quality. And that can make a big difference if you're reusing it. It can really improve your system longevity and, in many cases, efficiency, versus putting in dodgy old refrigerant that you're not too sure of its background or quality. Right, so key point, refrigerants are expensive, so getting the right deal for your situation makes a big difference. Now, the third point we wanted to really hammer home is that drop-ins are a compromise solution. They're not the final end goal, which is really more around the naturals that Dave was talking about. So the first reason that they're a compromise is that, in theory, they can reduce your capacity of your system and your efficiency. And that's generally thought to be due to the different properties of these drop-in replacements. They are different, and you can expect some differences, potentially around 0 to 5% loss in capacity and compressor efficiency. Now, where that would matter is where you're really tapped out on capacity, or you've got a really high utilization system where changes in efficiency make a big difference to your annual cost. However, as I said before, what did we find from the pilot trials? Well, we actually found that when you look at it from an energy system altogether, there was no real clear change observed across 14 systems that we were able to directly compare the before and after with from the 2025 season versus the 2026 season. There are some that potentially had a slight increase in total daily electricity use, but others had slight decreases. The key thing is, though, that any of these variations were really dwarfed by other factors, such as changes in evaporator fan speeds being a key one. So if you've got a cool store, for example, where you've got multi-speed options for your evaporator fans, which is what the case was on the right-hand graph here, then you can see this big step down is when they changed the evaporator fan speeds, and it happened later in the 2026 period. And that's why it drops later. But you can see that those sort of effects are vastly more significant than any difference between the years. And we haven't just cherry-picked these. This is roughly the same kind of thing across all 14 systems that we're able to directly compare. The next way in which drop-ins are a compromise is that there's an environmental trade-off with them. So you're reducing your emissions liability, your potential for emissions from leaks, but there is the issue around forever chemicals with the HFOs. And that is something that's kind of a subject of ongoing debate and investigation and potential legislation or regulation over in Europe. So, yeah, there is potential that they can degrade into these PFAS, forever chemicals, such as trifluoroacetic acid. And these have uncertain long-term health effects, but they have been identified as rapidly accumulating globally, and they're thought to primarily be due to refrigerants. So, yeah, I guess that's the question in red. Is it better than emissions? And that's really going to be a question that's probably the subject of ongoing discussion for some time yet. The point C here, that there is still a risk of significant emissions, particularly if you've got a small site with a large leak, because they do still have the hydrofluorocarbon component, which has a high GWP. So if you had an R449A leak quite badly from a moderately sized system, it could easily double your site's annual emissions from energy. So it's still a risk. It's just much less, about 2/3 less or so. And then the final point there, these drop-ins are generally expected to be phased out eventually, and there's proposals in Europe to regulate those products that I was talking about before that create the PFAS and the TFA, which is including HFOs, lots of acronyms there. And there's also the shrinking import limit that we talked about earlier on the HFCs that may make it harder to get or higher cost for some of these drop-ins because of the HFC component. So all that to say, it's not the ideal solution, but it can be a good solution for the right situation, a transitional solution to get old systems through to retirement. So that's the 3 key points. Drop-ins are a simple option to reduce the GWP of old systems and therefore reduce the impact of any leaks that do happen. Key decisions that you must make do have a big impact on the capital cost, particularly whether you decide to just go with mechanical valves or go with electronic valves. Refrigerant disposal and supply arrangements, getting the best deal there makes a big difference because those refrigerants are so expensive. And then just remember that the drop-ins are not the be-all and end-all, they're a compromise, and you should think of them really as a transition tool, not a final solution. All right, I'll pass back over to Chris.
Yeah, thanks very much, Tony and Dave, and actually a few others in the background for the considerable effort and thought that's been put into these studies. It's been great fun to be a part of it. Also want to thank MPI and G4 and our pilot participants for their invaluable insights. I know that Tony and Dave and others have really enjoyed working with the teams out there at the cool stores. We now have time for a few questions. So if you don't feel like we haven't formulated your question quite yet, then please do reach out at the email addresses that are here on the slides. The Q&A session should be on the bottom of the Q&A for the webinar should be on the bottom of your screen. So you can also submit a question there, and we'll try and get to those in a minute. The final reports are forthcoming. In fact, the report for Workstream 1 has been published on our website today, so that's the Deta website. We also have a report for Workstream 2, the Tony's work, that's to be published in September, and Tony's promised me that, so that's excellent. And we'll share today's slides with all the participants in the next couple of days. So we'll just send it out to the participants' emails, and we'll also publish a recording of this webinar at some point soon. And finally, just a sort of a watch out for the webinar for the Workstream 3, which is the final workstream for the project. That's the leak detection and mitigation. That work is ongoing, and the webinar is expected later this year, sometime just before Christmas.